Hello everyone. So in today's session, let us take up the continuous beam, for which we have considered a load which is acting for an overhanging span. Thereby we need to calculate the final end moments for this case by using the moment distribution method. Along with this, at joint B, I have considered the settlement of 10 mm. So by using all these considerations, let us start with the problem to calculate the final end moments. We shall go stepwise to calculate the fixed end moments. Before that, since E and I is given here, EI value is given, we shall calculate the value of EI, which will make our calculation easier. So what is E? It is equal to 200 GPa, which is equal to 200 into 10 power 6, and I is equal to 4 into 10 power 8 into mm. Convert this to meters, 10 power 3 to the power 4. So what is the value here? 4.8 into 10 power 4 kilonewton meter square. So this is the value of EI for which is to be considered for our calculation. Now we shall start with the procedure to calculate the fixed end moments. So for this we have a overhanging span of A dash A, of which load of 80 kilonewton is acting. So for this case, there is no need to calculate the fixed end moments, since we will get the final end moments directly. So for this span A dash, the final end moment is, that is the final end moments at A dash is equal to. So in case of overhanging, we consider the left portion as positive. That means we consider positive for left portion overhanging and negative for right portion overhanging, which is 80 into 2. Since it is the left portion, so the overhanging towards left is considered positive, which is equal to 160 kilonewton meter. So this will give you directly the final end moments. Next, we will go for the calculation of the fixed end moments for each span. So for span AB, MFAB is 0, which is equal to MFBA, since there is no extra load acting for the span AB. Next, for span BC, MFBC, since the load acting here is UDL, which is equal to minus WL square by 12, which is equal to minus, what is the load acting? 10, length is 4 meters divided by 12 minus 3.33 kilonewton meter. Then MFCB plus WL square by 12 plus 10 4 square by 12, which is equal to again plus 13.33 kilonewton meter. Now for MFCD, we have a point load as well as UDL. Okay. For span MFCD, initially we consider the UDL minus WL square by 12 minus W AB square by L square, which is equal to minus 224.26 kilonewton meter. Then MFDC plus WL square by 12 plus WA square B by L square. So here W is 20, length acting is again 10 square divided by 12 plus W40, A is equal to 6, 4 square divided by again length is 6, 205.0. So this is the value for MFCD and MFDC. So next we need to calculate the end moments by considering sinking or settlement. So to calculate the end moments by considering sinking, so we have this is gets sinking by 10 mm. To convert it to meter, it is 0.01 meters. So this is 4 meter, 6 meters. We even have a overhanging span of A dash for a particular loading. So we need to calculate the end moments by considering the settlement. For span A dash A, there is no effect of this settlement. So we don't need to consider this. And for this span, since final end moment itself is calculated, no need to further calculate here for the fixed end moments. Then for span AB, that is M dash AB. So M dash AB is equal to M dash BA is equal to, we have to consider the settlement here, since due to settlements there is change in the moment at A and B both. So as we all know, with respect to left support, right support is sinking. If the right support sinks with respect to left support, then the moment considered is negative, which is equal to minus 6 EI delta by L square. It is minus 6 into, for span AB, EI is 2 EI, 2 into EI calculated as 2.8 into 10 power 4. Then what is delta? Delta value is 0.01 meters divided by the length for span AB is 6 meters minus 160 kilonewton meter. Next, M dash BC equal to M dash C. For this, BC is the span considered, right. So with respect to right support, left support is sinking, therefore the moment considered here is positive, plus 6 EI delta by L square. So plus 6 EI is 3 into 4.8 into 10 power 4 multiplied by delta is 0.01 divided by, what is the length for span BC? It is again 4 meters. This is equal to, so here it is positive, 540 kilonewton meter. Now by considering MF values and M dash values, we obtain M double dash values, which is the net moments or net fixed end moments for this span. So finally the net moments is as we calculated M double dash AA dash, it is already calculated, which is equal to 160 kilonewton meter, it is positive. Then M double dash AB equal to MF AB plus M dash AB. So since there is no load acting, MF AB is 0 and M dash AB is minus 160 kilonewton meter, which is equal to minus 160 kilonewton meter. Then M double dash BA, even here There is no load acting, MFBA is 0 and M dash BA is again minus 160, which will give you minus 160. Then M double dash BC. So what is MFBC? It is minus 13.33 and M dash BC is plus 540, which will give you 526.67 kilonewton meter. Then M double dash CB equal to plus 13.33. Again M dash CB is 540 plus 540, 553.33 kilonewton meter. Okay. Finally, M double dash CD and M double dash DC. So MFCD is given by minus 224.26. Then there is no effect of the settlement at B for CD span. So therefore, the moment or the end moment due to sinking for the span CD is 0. Thereby the end moment or the net moment is equal to kilonewton meter. Then for M double dash DC plus 205.07 plus 0, since there is no effect on this span, which will give you 205.07 kilonewton meter. So these are the fixed end moments for all the spans. By using this, we need to now go for the next step, which is step 2, to calculate the fixed end moments. Step 2, to calculate the distribution factors by using distribution table. For this, consider the joint member stiffness factor, sigma k, and finally factor. So for this, let us start from joint A. Okay. Now at joint A, we have two members, A dash and AB. A dash and AB are the members at joint A. Then for this joint, we need to calculate the stiffness or the member stiffness factor, which is equal to K. So in this case, this span A dash, the stiffness K is equal to 0. For span AB, since for span AB, A is the near end and B is the far end. Here, since the far end is continuous, we consider this as fixed. Since it is fixed, we take this as 4 EI by L. So 4, what is EI for span AB? It is equal to 2 EI divided by what is the length here, which is equal to 6 meter, 1.33 EI. Then what is sigma k? 1.33 EI plus 0 will give you 1.33 EI. So at this A dash, again the distribution factor is 0 divided by anything is 0. So 1.33 EI divided by 1.33 EI is 1. Next, for joint B, we have two spans BA, BC. So for span AB, B is the near end and A is the far end. So when you consider this far end, this support A is not a continuous end, whereas it is the end support. Since the end support is hinged, we consider the stiffness value as 3EI by L. So which is equal to 3 into 2EI divided by length is equal to 6 meters, that is equal to just EI. Then for span BC, when we consider BC, B is the near end and C is the far end. Since the far end is continuous, we consider it as fixed. For fixed support, the value of K is 4EI by L. 4 into EI is 3EI by 4, that is equal to 3EI. Then sigma K is equal to 4EI. Then for span BA, it is equal to EI divided by 4EI, which is equal to 0.25 and 0.75. Next, for joint C, CB, CD. For CB, C is the near end, B is the far end. Since the far end is continuous, we consider it as fixed. So for fixed, it is 4EI by L. 4 into CB, it is 3EI divided by 4, 3EI. Then again CD. For CD, C is the near end, D is the far end. Since the far end is fixed, it is 4EI by L. 4 into EI is 10EI divided by, what is the length? 10 meters, that is equal to 4EI. The sigma K is equal to 7EI, which is 3 plus 4. Then 3 divided by 7 will give you 0.43 and 4 divided by 7 will give you 0.63. So this is the distribution table to calculate the distribution factors for all the joints. Next is to calculate the final end moments by using the moment distribution table. So next is the step 3, which is moment distribution table. For this, we have joint, so we have 4 joints A, B, C and D. Then members AA dash, AB, BA, BC, CB, CD, then DC. 0, 1, 0.25, 0.75, 0.43, 0.57, and finally the distribution factor for the fixed support is 0. Okay. Now write down the fixed end moments calculated: plus 160, minus 160, minus 160, 526.67, 205.07. These are the fixed end moments. So next, to balance these moments. So for joint A, we have moments of 160, plus 160 and minus 160. So when you balance this, plus 160 and minus 160 will become 0. So 0 multiplied by 0 is 0 and 0 multiplied by 1 is again 0. Next for joint B, minus 160 plus 526.67 will give you 366.67. So plus 366.67 is the unbalanced moment. To balance this, minus 366.67 minus 366.67 into 0.25 will give you minus 91.67. Again, plus 366.67 is the unbalanced moment. To balance this, minus 366.67 multiplied by 0.75 minus 275. For joint C, 553.3 minus 224.27. So when you consider these two, 329.06. So plus 329.06 is the unbalanced moment. In order to balance this, we need to consider minus 329.06 multiplied by 0.43 minus 141.5. 329.06 multiplied by 0.57 56. So this again 205.07 is the unbalanced moment. In order to balance this, we consider minus 205.07, which is multiplied by 0 will again give you 0. Carry over moment. So the carry over moment is to be considered for each joint. So for joint A there is no moment to carry. We can directly go for joint B. At joint B, so at joint B towards span BA, here the moment acting is, the applied moment is minus 91.67. So this minus 91.67, when it is transferred to the other side, if it is fixed, will be half of the moment. Since the far end is hinged, there is no moment transferred to this span AB, thereby we can directly consider this as, that means we can directly consider the final end moments for AA dash and AB as plus 160 and minus 160 kilonewton meter. Okay, the further procedures may not be considered for the span AA dash and AB. So we have to carry it for B and C. For joint C, where we have two spans BC and CB. So for span BC, the applied moment at B is 275.5. So half of 275 can be transferred if the other end is fixed. Since it is continuous, we consider it as fixed. So half of 275 is transferred to CB minus 137.5. Again for CB, the applied moment is 141.5 in the anticlockwise direction. So half of 141.5 can be transferred. Since the other end is continuous, we consider it as fixed. So half of 141.5 is minus 70.75. Okay. Then for CD, the applied moment is 187.56. Half of this can be transferred to the other end if the far end is fixed. 0.78. To balance this, for joint B, we have BA and BC. The value is minus 70.75. This is the unbalanced moment. To balance this, we need to consider plus 70.75. So plus 70.75 multiplied by 0.25 will give you plus 17.63. So minus 70.75, to balance this, plus 70.75 multiplied by 0.75 will give you 53.06. Here even for the next joint C, we have CB and CD. The moment is minus 137.5. To balance this, plus 137.5 plus 137.5 multiplied by 0.43 is, then again plus 137.5 multiplied by 0.57. Carry the moments. So This procedure or the carryover moment is done for from BC to CB, CB to BC and CD to DC only. So, we will continue the procedure only for these spans. So, what is half of 53.05, 26.53 and half of 59.12, 29.56, then half of 78.38, 0.19, 39.19. Next again the balancing step. 29.56 is the unbalanced moment. To balance this, minus 29.56 into 0.25 is minus 7.39, minus 29.56 multiplied by 0.75 minus 22.17. 26.57 is the unbalanced moment. To balance this, we consider minus 26.57 into 0.43 minus 11.41 minus 26.53 multiplied by 0.57 minus 15.12. Carry over moment is carried only for this. Half of minus 11.41 minus 5.7 and half of 22.17 is 11.08. Half of 15.12 is minus 7.56. Balance this. Minus 5.7 to balance this, plus 5.7 into 0.25. 5.7 into 0.25 will give you 1.42 plus 5.7 multiplied by 0.75, 4.28. Minus 11.08 is the unbalanced moment. To balance this, plus 11.08 into 0.43 plus 11.08 multiplied by 0.57. Next, carry over moment, carried only here. Half of 4.76 is 2.38. Half of 4.28 is 1.4. Half of 6.32, 3.16. Next is to balance. For BC, 2.38 is the unbalanced moment. To balance this, minus 2.38 multiplied by 0.25 will give you minus 0.59. Minus 2.38 multiplied by 0.75 will give you minus 1.79. 2.14 multiplied by 0.43 will give you minus 0.92. Minus 2.14 multiplied by 0.57 will give you minus 1.22. Next, carry over moment. Half of minus 0.92 is minus 0.46. Half of minus 1.79 is minus 0.895. For CD it is minus 0.61. Next is to balance. Minus 0.46 is the unbalanced moment. To balance this, plus 0.46 multiplied by 0.25 is 0.115. 0.46 multiplied by 0.75 is plus 0.345. 0.89 into 0.43 is 0.384 and for CD 0.510. Next, final end moments. The final end moments for A dash is plus 160, AB minus 160, for BA minus 240.4, for BC it is 240.41, for CB it is plus 342.96, CD minus 342.96, DC 145.57. We shall start with the next step, which is the step 4, which is to calculate support reactions and maximum bending moment. For this, let us take up each span separately. So initially for span AA dash. So since it is the overhanging load and it is A, this is A dash acting for a distance 2 meters. Here you need to calculate the reaction at A, which is given by RAA dash. For this, since the load acting here is 80 kilonewton, so we shall consider this condition of upwards forces as positive. So since the load of 80 kilonewton is acting downwards, I take it as negative minus 80 plus RAA dash is equal to 0. Then RAA dash is equal to plus 80 kilonewton. Since it is positive, I consider the direction as upwards. So this is the reaction at A for span AA dash. Next, for span AB. So for span AB, these are the supports. Even here it is AB. For this, there is no extra load acting. We have to consider only the moments. So from our calculation, the moment at A is given by 160 kilonewton meter, and at B, it is BA is 240.4 kilonewton meter. For this, I will consider the condition sum of all the forces at A is equal to 0. Since the loads acting here are RAB and this is RBA. So this 160 is acting in the anti-clockwise direction, so I consider it as negative, and this 240 kilonewton, 240.4 at B is acting in the again anti-clockwise direction, minus 240.4, and this reaction at B, that is RBA, is acting at a distance of say 6 meters. It is minus RBA, since it is acting in anti-clockwise direction, into 6 is equal to 0. From this we get the reaction at B minus 66.73 kilonewton. Okay. Then one more condition, sum of all the forces upwards, sum of all the vertical forces is equal to 0, upwards positive. So for this, so we have only two vertical forces, that is RAB and RBA, it is equal to 0. Therefore RAB is equal to minus of RBA, therefore it is plus 66.73 kilonewton. Since it is negative, we consider the sign. Okay. Next, for span BC. BC 10 kilonewton per meter and the distance is say 4 meters. what are the loads acting, that is the moments at the ends, which is equal to 240.4, 342.9 kilonewton meter. So for this also, sum of all the moments at B is equal to 0, clockwise positive. So what are the loads and moments considered for joint or the point B? 4 kilonewton acting in the positive direction. So then minus 10, this 10 into the distance 4 multiplied by half of the distance is acting in the, so here 240.4 kilonewton meter, it is acting in the clockwise direction, therefore positive 0.4. This load, the UDL of 10 kilonewton is acting at a distance for a span 4 meters. So 10 into 4 divided by half of its distance, it is 4 divided by 2 is again 2. Then again plus 342.92. Here we need to calculate RCB and RBC. RCB is acting in the anti-clockwise direction, multiplied by 4 is equal to 0. Yes. RCB is equal to minus 165.84 kilonewton. Then, so RCB is equal to 165.84 kilonewton. Then considering one more condition, sum of all the vertical forces is equal to 0. So here the vertical forces are RCB plus RBC is equal to 10 into 4. So we need to calculate RBC. 40 minus RCB is 165.84 minus 125.84 kilonewton. This is RBC. So acting downwards. The last span for span CD. So for this case, we have two types of loads acting at a distance of say 10 meters. Okay. So at C, we have a UDL. This UDL is 20 kilonewton per meter, and along with that you have one more load of say 40 kilonewton acting at a span of 4 meters. So even here we need to calculate RCD and RDC. So for this, I will write it here. Sum of all the moments at C equal to 0, considering clockwise as positive. So we need to even consider the moments. The moments are 342.9 kilonewton meter and 145.47 kilonewton meter. This is the clockwise direction and this is in the anti-clockwise direction. So for this, the moment at C, sum of all the moments at C is equal to 0. So this 342.9 kilonewton meter is acting in the anti-clockwise direction. So I take it as negative. Then this 40 kilonewton multiplied by the span 4 meters, which is in the clockwise direction, plus 40 into 4. Then again this 20 kilonewton. So this UDL is acting for the entire span CD for the distance of 10 meters. So this is also acting in the clockwise direction. So I take 20 into 10. So half of this distance will give you 10 by 2, which is 5. Okay. Then this 145 is also acting in the clockwise direction. Then again finally RDC is acting in the anti-clockwise direction into multiplied by the 10. So totally the reaction at DC, that is RDC, is given by 96.31 kilonewton. Since it is positive, I consider the direction as upwards. And one more condition, RCD plus RDC is equal to 40 plus the UDL is 20 multiplied by the distance is 10. So finally what is RCD? 143.68 kilonewton. This is also positive. We take it in the upward direction. For this span, we need to calculate the maximum bending moment. As we all know, the maximum bending moment will be at a point where the shear force is 0. So to locate the point where the shear force is 0, we need to consider the shear force diagram. So for this we need this space, so I just write down these values here. RCD is 143.68 and RDC is 96.31 kilonewton. Now to draw this, by knowing the reactions at CD and DC. So what is reaction at C? So RCD is given by 143.68, which is positive. So it will be somewhere here, kilonewton. 143.68 minus 20 into 4, that is 80, will give you 63.56. So that is will be acting at this point. Okay, 63.68. This is 63.68. So at this point again minus 40. 63.68 minus 40 will give you 23.68. Okay. After this, at F, between F and D we have a UDL of 20 kilonewton per meter. So this 23.68 minus 20 into the distance is 6 will give you 96.44. So this, since it is UDL, take this variation. .32. Okay. Now this is the point where the shear force is 0. So at this point we need to calculate the maximum bending moment. This I consider it as F. To calculate this distance, we need to consider these two triangles, for which the distance I consider it as X, and this will be, the overall distance is 6 minus X. So from this similar triangles, X divided by 23.68 is equal to 6 minus X divided by 96.32. Therefore, the X value is 1.18 meters. So to calculate the maximum bending moment at F. So moment at F when I considered towards the left support is equal to, we have considered 342.9 acting in the anti-clockwise direction, so it taken as positive, so taken as negative. Then UDL of 20 kilonewton acting at a span of 5.18, 20 into 5.18 into 5.18 divided by 2 minus 40 into 1.18. Then this RCD is acting in the clockwise direction at a distance of say 4 plus x, which is equal to 5.18. Therefore, the moment at F 0.8 kilonewton meter. So this is the point where we get the maximum moment and it is equal to 85.8. So after calculating these reactions at each joint, now we need to draw the Sfd and Bmd, that is shear force diagram and bending moment diagram should be drawn. For this, initially let us draw the shear force diagram. Now for the span A dash A, for A dash A, since 80 kilonewton load is acting downwards, the load is minus 80 kilonewton. Then reaction at AA dash, that is RAA dash is again given as minus 80 and plus 80 will give you 0. Then reaction at the span AB, that is RAB. For the span AB, the reaction at AB is given by 66.73. So plus 66.73 comes somewhere here, 66.73 kilonewton. So join this. Then in between A and B there is no load acting, so I take it as constant. At B, for span BA, that is RBA is given by minus 66.73. So plus 66.73 minus 66.73 will be 0. So now next, for joint B, for span BC, reaction at BC, that is RBC is given by minus 125.84. So minus 125.84. So we have to take below the neutral axis. So it comes somewhere here, that is 25.84 kilonewton. So in between B and C, we have a UDL of 10 for a span of 4 meters. So minus 185.84, this load is also acting downward. So minus 185.84 minus 40 will give you minus 165.84. Then the reaction at C, that is RCB is given by plus 165.84, therefore it is 0. Next, for span CD, what is the reaction at RCD? 143.68. Then, so at this point F, 40 kilonewton is acting. So in between C and this point F, there is load of 20 kilonewton, which is UDL. So 20 into 4 will give you 80. So 143.68 minus 80 will give you plus 63.68. So plus 63.68 minus 40 is 23.68. Then between F and D, it is 20 kilonewton acting at a span of 6 meters. So 23.68 minus 20 into 6, it is 120, will give you 96.31. So join this. Okay, this is the shear force diagram. This is negative, positive, negative, positive and negative. This is also positive. Okay. Now, this is the shear force diagram. Next, to draw the bending moment diagram, draw the bending moment diagram, we need to consider each span. So, between A dash there is no moment acting, therefore the moment at A dash is 0, and at A there is a moment of 160 kilonewton meter is acting towards right. So, the moment acting towards the right side of the section in the clockwise direction is considered as negative. So, we take 160 as take 160 in the negative direction. So, the moment for AB, the moment acting in the left side in the anti-clockwise direction is again negative, which is already done. Next, for joint B, the moment of 240.4 kilonewton meter is acting. It is acting in the anti-clockwise direction in the right side. So, the moment of 240.4 kilonewton meter acting in the anti-clockwise direction at the right side of the section, therefore, we take this as positive. So, this will come somewhere here, which is 240.4 kilonewton meter. Then at C, 342.96, so it is acting at right side clockwise is negative. So, we have to take this below, it is 342.9 kilonewton meter, and between C and D. So, now in between this, so the load acting is UDL, therefore, we join it in terms of a parabolic. So, in between B and C, since the load acting is UDL, so we have shown the parabolic variation. Okay. So, in this particular section, see in the shear force diagram, there is no change in the point of contraflexion. That means the shear force is not 0 at any point. Therefore, we will not be able to know the exact point where we get the maximum bending moment. So, we have not calculated for this span BC. Okay. Now, between C and D, this is the point where we get the maximum bending moment since the shear force is 0. I have considered the point F. So, here we can mark for the maximum bending moment. Before that, we have the end moments, that is 342.96, which is acting in the anti-clockwise direction. So, left side anti-clockwise is again negative, which is already done. Then at D, 145.47 acting in the clockwise direction at the right side. So, in the right side, the moment acting in the clockwise direction is again considered as negative. So, the moment is 145, somewhere here, 145.47 kilonewton meter. In between these two, the maximum bending moment is calculated at point F, that is equal to 85.8, which will act 85.8 kilonewton meter. Okay. So, this is the point where we get the maximum bending moment. Okay. So, this is the Sfd and Bmd for the continuous beam with a load of 80 kilonewton at the left span, which is overhanging. Then we have even considered settlement at point B, which is of 10 mm. Okay. Thank you.